Okay, so same analysis before. Muddy's Point due this Sunday. Concept check 3B due at the Sunday at the end of spring break. Mini project 3 due the Sunday after that. And then the two-person team elections do that Saturday, after spring break. I do that during Saturday just so that it gives me sort of time, a little more time, so that if there are any stragglers that I kind of bring teams together manually to inform those teams. So I'm sure that everybody's got enough time, because after the teams are formed, there's like a week where you have to submit a very, very short submission which says which algorithm that you'd like to work on. And so I want to make sure that we've got enough time and the teams together for you to make those decisions. All right, any questions about the stuff coming up? So we left off, transitioning from multi-objective optimization to multi-modal optimization, and mentioned that a key point in both of them is that in multi-objective optimization, we want a continuous spread across the Pareto frontier. And that's something that Pareto ranking doesn't give us for free. In fact, it creates challenges to that, because if everything's equal fitness along the Pareto frontier, and you use a drifty selection operator like tournament selection, then what's to keep everything from collapsing to a single point? And even if you can manage to maintain your existing diversity, what if it happens to be pretty clumped? How do you try to not only promote moving toward the frontier, but moving along it? And then similarly, in multimodal optimization, we have these discrete peaks that we want to make sure that we're on. And so when you have individuals on a peak, you want them to climb up that peak. So you do want a general, for every individual on that peak, a general pressure to all go to the same place. But you also want to have pressure for kind of global scale diversity. So somehow we want both individuals on a peak to want to run up the peak, but when there are too many individuals on that peak, have individuals that want to go across that peak. So that's why we need these diversity preservation methods, which are sometimes called niching methods. The niche analogy works really well in the multi-objective, because that is exactly what niches are in community ecology. They are different combinations of traits that give a different species the ability to coexist with other species that have been partitioned out into different niches. So there are different trade-offs. So this species achieves high reproductive success by having a certain set of traits based on vision. This other species achieves higher reproductive success by having another set of traits based on olfaction. Now, there might be developmental constraints in the brain that prevent having both of those simultaneously, thus creating a physical trade-off, making it possible to only have one, meaning creating the opportunity for a niche separation. And that's how we get community ecology. That's why we get, some things that, plants use the sun. That's how they get their energy. Animals eat the plants. Other animals eat other animals. Animals, some live on the ground, some fly. None of these are an optimal body plan. These are all different options for achieving reproductive success in a complex environment. And that's really what the Pareto frontier represents, is different options for doing that. And then each one of these, you can think of different species that dominate their local niche. So that niche works really well here. It's a little harder to see that here. This is certainly niche-like, or I guess as the kids would say, it's giving niche, but it's not quite like the same sort of trade-offs, because we just have one objective. So it's like we have one trait, but we see that there are multiple different ways to achieve high fitness in that trait. So sometimes these are still called niches, but I was hesitant to call them niches because niche really implies trade-off. And it's hard to say there's a trade-off when you only have one objective. Now, in reality, when you present the output of multimodal optimization to a stakeholder, there often then become discussions that become like multi-objective. Because once you show your stakeholder that there are these three options that all have similar fitness, similar performance in the thing that they said they cared about, then they start asking themselves, how do I sort these? And then it turns out there's something else they cared about that they didn't share with you initially. And now that we know that other thing, then they can then start sorting these. So it turns out there really is a multi-objective there. The niching thing, so that's why people will call this a niche, call this a niche, call this a niche, but it's not quite there, but they're certainly niche adjacent. So point is, for all of the multi-objective algorithms we have, you usually can bolt on a different diversity preservation metric. And for all of the multimodal, you can bolt on a different diversity preservation metric. So today, we're going to talk about the different classes of these diversity preservation modules. And if you look through many different multi-objective evolutionary algorithms, you'll see that they might bolt on an elitism method that you've heard about before, and they might add in some of this diversity preservation. So I'm not presenting these in the context specifically of multi-objective or multimodal. These are meant to be general purpose tools you could use for both. In rare cases, there'll be one that only applies to multimodal or only applies to multi-objective, and I'll highlight those. But so today we're focusing on how do we achieve this in kind of either context. All right, so that's the background. So there are these four basic categories. These are in a slightly different order than I presented them before. I'm not going to go into great detail here. This is the same content you've seen before. We're going to drill down into each one of these categories today. So they've basically been into ways of updating fitness in order to downstream adjust selection dynamics. So when you're calculating fitness, you look at the population, and based on the density of the population, you update fitness. And an alternative is leave fitness alone and then change the way you do selection. And so your selection criteria will be primarily based on fitness, but then it might have tie breaking, for example, that's based on crowding, spacing, things like that. Another option is archival methods, where you focus more on how many really good solutions you found and use that archive, or that, which is sort of like elitism, this one version of that, look back at your archive, and then based on that archive, change how you admit new members to that archive. So if you notice that I've got a bunch of members that have a certain set of properties already in my archive, then I might not admit more to that if they're too close to them in that archive. And then the population structure methods, which we'll talk less about today, and a little bit more as we go into parallel and distributed GAs next time. But these ones sort of decompose problems into separate little subspaces and then run algorithms in parallel that may communicate a little bit, but that initial decomposition helps enforce diversity from the start. Question?
So archival is just memoization?
No, it's memoization is certainly important when, so memoization is the idea that if I've already calculated something once for a certain set of inputs, I store that in a lookup table so I don't have to pay the cost of the calculation another time. And that is a great way to optimize a lot of these multi-objective evolutionary algorithms, because they can come back to something they've done before. And so if it was a very costly black box function that takes a long time to run, if you put the same inputs into that function, you've already run it before, then just skip the function and just go back to that's a sort of type of archive. Here I'm focusing on not archiving everything, which would be kind of memoization, which is kind of a caching method. But this is focused on like non-dominated archive. We'll see an example of a species conservation GA that does this, but we've already seen this a little bit in elitism in general is a class of this, but when we've seen these non-dominated sets that accumulate in parallel with some of these multi-objective algorithms, that's an example of this, where the point is you're not archiving everybody, you're archiving just the best you've seen so far, and then you might use the population of that to say, wow, you know, so far we've really got really good coverage on this side of the Pareto frontier. So, you know, we notice that we've got really good coverage down. We don't know what the Pareto frontier looks like. That's kind of the point, but everybody in our archive all seems to be very similar to each other. So given that, you know, we've got this covered, we know that this is probably a part of the frontier, then maybe as we start generating new solutions, we try to make them different from those in the archive. So you sort of force them to be different in the genotype space so that hopefully after they go through the selection processes, they land at a different part of the frontier in the case of multi-objective. So that's the idea of the archival methods adds a different layer of feedback where you use the progress you've made to sort of inform where else to search. But we'll see an example of that. But yeah, so these are the major categories here. And a key thing in all of these is that they're enforcing a type of density dependence. So or in other terms, it's a frequency dependence. So far, if we just think of all of these, really so these were the sort of the first diversity preservation methods, and these will be the first ones we'll talk about, and where they modify fitness. So the original version of fitness that we had was somewhat not biological in that it didn't matter who else was out there in the population. Fitness was just based on the optimization objective given to you by the person who threw down the design problem. And it didn't matter what the rest of the population looked like. Now in biology, the number of individuals that are currently in a certain area of the trait space sometimes does matter. So sometimes your fitness is not just about how well you can eat a plant or how well you can find an animal, but it's how well you can do that relative to others. If everyone is doing it the way you're doing it, then if there's an alternative thing that you could do, that might become advantageous. And so that idea of frequency dependence, if we can add that to our notion of fitness here, so that it's not just about the objective, but it's about how much coverage that point of the trait space has, then we can start spreading individuals out the same way we see in nature. And so this is what I'm saying here. It creates what we call negative frequency dependent selection. So it's frequency dependent in that the fitness will be negatively related to how many already exist in that area of the trait space. So rarer solutions gain a little bit more fitness. That's what makes it negative. So the more that have it, the less beneficial it is to have it. So that's what I mean by negative frequency dependence. So this is like, let's say there's, if we're thinking about sexual selection, for example, it might be the rarer color will end up getting more attention. And so it might be that, if everybody has blue eyes, then maybe blue eyes doesn't end up having a lot of advantage when it comes to matings. But if blue eyes is a rare phenotype, then maybe it gains an advantage. If you have that negative frequency dependent selection, then that helps explain how you might get different eye colors that all appear to have the same overall fitness, like they all can see the same. But if there's this additional sexual pressure, which creates a negative frequency dependent fitness or negative frequency dependent selection on it, then you might stabilize multiple eye colors at particular sort of subsets of the population. So you might have, if you have 4 eye colors, they might be equally distributed across the population, because once any one of them becomes more popular, it then has a fitness hit and it brings it back down. So you get a natural regulation where now you see all of those phenotypes being equally represented. And we like that when we're designing these algorithms, because for multimodal optimization, we don't want everybody just going to the highest fitness peak. Once we have enough there, we want the rest of them to start spreading out. So that's what we want to engineer into our artificial populations. So when we think about nature and negative frequency dependent selection, the first place we go to is game theory, because evolutionary biologists use game theory to think about these things. And so here's another game, the hawk-dove game, otherwise known as the chicken game. There's a couple other names for it as well. So you imagine you have two players, and they can play either of two phenotypes. They can be aggressive, or they can be kind of more submissive, so they can fight or they can share. And we're going to call the fighting one hawk and the sharing one dove. And so if two hawks fight each other, then, so I've got these W, T, L, and X, win, tie, lose, and I don't know, you could call it death is the X. So X is really bad. So if two aggressive individuals meet each other, then they just fight. They do not share resources, and then they suffer a huge cost, a huge penalty. Now it's in contrast that if a hawk meets up with a dove, if there's 10 resources, 10 units of resources on the line, the hawk will just get all 10 of them. The dove will go away with none, but at least the dove survives to fight another day or to give up another day. So the dove shares with the aggressor and shares everything with the aggressor because the aggressor is so aggressive. But if two doves meet each other, they just split things equally. So you can kind of think there's a resource of 10 here, and it's either being taken entirely by the hawk, or it's being split in half by the dove-dove combination, or if two hawks fight each other, then they expend so much energy fighting that they end up coming out at a negative. So in some ways you can say, oh, it's better to be a hawk, but it's not better to be a hawk if everybody else is a hawk. Because if everybody else is a hawk, you're guaranteed to get into a lot of fights. At that point, then sometimes it's better to be a dove, because at least, even though a dove is going to give away everything to a hawk, then you're at least going to survive, and potentially, if there happens to be a couple other doves out there, then if you happen to sometimes run into doves, then it will be better, then you both will end up getting the ability to share those resources. So I hope you're seeing there's going to be a frequency dependence which comes into that. If I just look at this matrix as it is, I see there are two so-called pure Nash equilibria. They're the ones that are highlighted. So you can, if you go through the exercise, you can see this one is Nash and this one is a Nash. So if you happen to live in a world where these two players, one of them is a dove and one of them is a hawk, there is going to be no benefit for either player to make a unilateral change. The dove isn't going to want to become a hawk, because now hawk versus hawk, that's really bad. But then a hawk isn't going to want to become a dove, because then they'll have to share with the other dove. So it's better for the hawk to stay hawk, it's better for the dove to stay dove. So this is a Nash. And so is this a Nash for the symmetric reasons. But this symmetry creates a problem, because then even though we can build lots of evolutionary games where we have phenotypes that look this way, who gets to be the hawk and who gets to be the dove? So there are some times where this also describes a traffic light. So at a traffic light, the one who gets to drive through the traffic light, they are the hawk. The one who has to sit and wait for them to go through the intersection, they are the dove. What breaks the symmetry, so-called correlated equilibrium, is the light. So once you introduce the light, the question doesn't be, do I play hawk or do I play dove? It's, do I play the thing the light tells me? And it is really bad to deviate from what the light tells you. And so if the light tells you to be a hawk, if you're a dove, then everybody's just going to sit there. So that means if you're going to stop at a green light. If it tells you to play dove, so it gives you a red light, then you better play dove, because the others have no reason to not play hawk. So you're going to pull into that intersection, you're probably going to get hit. So that's how you break the symmetry. Sometimes there's some correlated equilibrium. In natural systems or in biological systems, we see this. There will be certain physiological cues that create asymmetries, and say the one with the bigger eye stalks will always play hawk. But sometimes there is no way to break the symmetry. And that creates a conundrum we're figuring out, well, so what's going to happen? So what happens when you have no way to break the symmetry, decide who's going to play the hawk and who's going to play the dove? Then turns out there is an alternative Nash that exists for this system called a mixed Nash equilibrium, which means that the population will, a certain fraction of the population will play hawk, a certain fraction of the population will play dove. Or another way to view that is every individual will sometimes play hawk and sometimes play dove. The amount of times that you play hawk or dove, or rather the amount of the population that plays hawk or dove, I'll get that question in a second, is going to be determined by the payoffs. So there is some stable fraction. And this goes back to my original narrative, where if you're all hawks, if the entire world is hawks, it's actually better to be a dove than to be a new hawk, because that helps guarantee you don't get into these really aggressive and bad outcomes. So there is some natural regulation that will occur, and based on how much higher W is over T, then you can maybe get 75% hawks. That's maybe the equilibrium that stables out. Maybe it's 65, maybe it's 25. So it depends on the payoffs, but the point is you get a coexistence of the two strategies. Is there a question?
So in this situation, if you were to split it up in the risk versus Pareto efficient, here it would be more risk efficient to go dove, and hawk would be Pareto optimum.
Well, so there is not a, we don't have a, what you're thinking of, like in the stag hunt, there was a clear payoff dominant and risk dominant. There were two points that had that asymmetry between them. But here we don't, and so if we want to talk about who's Pareto, there are Pareto efficient points here. So remember, so does anybody want to guess, like what is one Pareto efficient outcome? Which one? Dove. So why do you say that that's Pareto efficient?
Because there's no way for anyone to change without also decreasing like that.
That's right. So there's no way. So the reason this is Pareto efficient is because if you switch to any, like if you go up so that the red player increases their payoff, then the blue player decreases their payoff. And likewise here, if the blue player increases their payoff, the red player decreases their payoff. And then here, nobody increases their payoff. So this is Pareto efficient. But there's, and this isn't even a Nash equilibrium. But if you think about it here, there's, in this case here, if the blue player increases their payoff, then the red player has to decrease their payoff. And likewise here. So you actually have three Pareto efficient, so this is the Pareto frontier, these three down here. But only two of them are Nash equilibria. And these two Nash equilibria, and this, by the way, is an example of an anti-coordination game. So the stag hunt was a coordination game where the two Nash were them doing the same thing. This is an anti-coordination game where the two Nash are them doing opposite things. And whereas in the stag hunt, the two Nash had this nice asymmetry that we could then label as payoff dominant and risk dominant. In this one here, there's not the same. That's the whole problem. There's too much symmetry, and that's what leads to the mixed Nash being the thing that we look for. And so you're going to end up getting a fraction of hawks and a fraction of doves, and that's going to be a smooth scale where exactly what fraction is stable depends on the numbers in the matrix. Yeah.
Would this game put it in a cycle of high dove population, high hawk population, low dove population means they all fight hawks or like to fight each other?
So that can happen. So if I have time and I have percent hawk, due to negative frequency dependent selection, you can get oscillations, undamped oscillations evolving. So you can get these things happening where you get high, it's almost like predator-prey oscillations, where you get high hawk, and at that point it becomes advantageous to be a dove, high dove becomes advantageous to be a hawk, and so on. It turns out that these often get damped by just natural phenomena, and so they end up sort of there being an exponential envelope, and so they settle out. There are some examples that is getting sort of outside of the scope of this discussion, but there are some great examples, like there's a lake in Africa where there are these two fish. Well, there's one species of fish that's a parasite, and its mouth either develops on the left side of its head or the right side of its head, and it eats scales off of another species of fish. And it sneaks up onto the other ones and then bites a scale off the fish. And it has to do it very fast. And so it's got this mouth that's on the left side of its face, so it can swim up next to it and just kind of pop over and pull that scale off. But eventually, the hosts, the fish that are getting their scales ripped off of them, start, whenever they feel a little tickle, they will have a bias that they'll then turn left or turn right. And if they turn towards the parasite, they can see the parasite, scare the parasite off, and they can prevent from getting the scale eaten. So there ends up being a negative frequency dependent selection where if there's a bunch of left mouth parasites, it becomes advantageous for right mouth parasites to be there because all of the hosts turn to look at the left mouth parasites, and that creates an opportunity. And they've been sampling this lake for decades, and they come back, and there's like a 2-year cycle where you come there in 1981 and you find a bunch of left mouth fish. You come back in 1982, you found a bunch of right mouth fish. 1983, left mouth fish, and then it keeps going on. And so it keeps oscillating back and forth, back and forth. So in that system, it doesn't ever damp out, and you get this stable limit cycle, stable sort of oscillations. In a lot of hawk dove games, I think it does stabilize out, but it really depends on other things that aren't modeled in the matrix, how the dynamics work. Yeah, but oscillations in populations, that almost always means there's negative frequency dependent selection. There's negative feedback. And so, in a control system, negative feedback is what can lead you to oscillations. Positive feedback drives you to a rail, but negative feedback, if it's not stable, can lead you to oscillations and even growing oscillations. Okay. All right, so this is one way we can try to think about, this is, if we really want to be faithful to evolution, genetics, for our diversity preservation mechanisms, we should try to involve something like this. But this doesn't feel like what we want because it involves these two discrete phenotypes. And whereas Gesundheit, in the Pareto optimal case, we want to spread that thing uniformly across this manifold, this Pareto manifold. And in the multimodal case, we do have discrete kind of phenotypes that we want to stabilize in the population. We don't know how many of them there are. They're spread around, and it's hard to sort of say well, hawk has this payoff and dove has this payoff. So how do we make a generic one where ahead of time we don't know what the discrete modes are? We just want to know that of the modes that we see out there, maybe based on the fitness peak, maybe that makes the mode more or less attractive. But we want to stabilize on the modes that we discover, not on modes that we impose with the game. So that's why fitness sharing really looks a lot more like something that I started talking about last time, habitat selection. And so this is not a generational timescale in the biological sense. The inspiration comes from this at a much shorter time scale, not even life history, developmental time scale. This is like a second by second time scale. So the idea here is to ask, in a continuous landscape, there are a number of discrete patches, so that's instead of niches, that have density dependent rewards, and that creates our negative frequency dependence. So this comes from a so-called scramble or interference competition. These are related things where this can happen here, where in scramble competition in particular, you have sort of too little, and I'll call it fitness, but you could say food. But there's too little reward at each peak, so in my multimodal case, but in each location where that reward can be distributed to support everyone in the population. So that means that once you get enough individuals at one location that provides reward, you end up using up all of the reward. And so the only thing the other individuals can do is to go to another location. And so the example I started talking about before were ducks on a pond or in a pond. And so I've got these 11 ducks, and if I sit there, I can watch them allocate themselves over time to different locations based on who's available. So this is beautiful for thinking about fitness sharing or think about a very general mechanism. As an engineer, I love this because I don't ever have to reprogram the ducks. The ducks have firmware that's constantly running. And if I put different people around the pond, different numbers of people, after a short transient period, they all automatically reallocate based on the sort of fitness or based on the relative quality of the different people throwing in breadcrumbs. And so that's why if I can make a diversity preservation mechanism that mimics what these ducks are doing, then it's going to be a great thing for me to implement in my genetic algorithm, because then my population members, they're going to be sensitive to fitness just the way that the ducks are sensitive to the breadcrumbs. So the breadcrumbs are like fitness, but they're also going to be sensitive to how many other individuals are exploiting that fitness opportunity. And it'll just naturally run in the background. So I can apply any optimization objective and it'll rebalance automatically without me having to do a lot of engineering of hawk-dove-like rewards. So, that's this. So finite population of ducks, they have discrete locations with different rates of reward, and each new duck at a patch reduces the reward that other ducks experience there. That's the idea. So in the multimodal version of that, so if I want to translate that to a multimodal optimization problem, then my decision variable is my position around the pond. And so here it's a one-dimensional position, but it doesn't have to be. So this could be any dimensional decision space you want. And then I've got these multiple fitness peaks with one objective, and that one objective is breadcrumbs. So what I'm really seeing here is what if there was a single duck in the pond, how much food would they get as they got close to each one of these positions? So as they're right, positioned in front of the person throwing out the breadcrumbs, they get a lot of breadcrumbs. Maybe a little bit next to them, they get some breadcrumbs, but it's really optimal to be right in front of that person. So that single duck, this is what they experience. But as you get more and more ducks at each one of these, you divide down that breadcrumb rate. So 10 breadcrumbs a minute, if there's 2 ducks there and each one of them have an equal chance of getting the breadcrumbs, each duck feels 5 breadcrumbs a minute. And so that divides that down. And so the study of under this system, or the description of the predicted allocation of animals in this position, is called the ideal free distribution, the IFD. And it can describe ducks in a pond, but it also can describe larger scale phenomena. It's ideal because you assume the animals have some way of learning where the fitness peaks are and learning it quick. And it's free because you assume the animals are free to move. And so the ideal free distribution, how they solve for this distribution is to introduce an individual level fitness concept called suitability. So this is our frequency dependent fitness. So a suitability is the reward to each individual in a patch that has a certain occupancy. So as the occupancy increases, the reward to every individual in that patch decreases. If you're familiar with the tragedy of the commons and those sorts of things, you can model tragedy of the commons problems with suitability functions as well. So the highway is really great for me as long as I'm the only one driving on it. Once other people start driving on the highway, there's congestion. It reduces the reward to every one of us. And if all you have is one highway, then you get the tragedy of the commons where at rush hour, there's so many people on the highway that the highway is no faster than the side streets. That's the tragedy. But the IFD will hopefully avoid the tragedy of the commons because there will be additional places for animals to go, other highways, other routes, and that will hopefully prevent them from saturating so that still highways will be better than side streets. Anyways, that's the general concept. We plot them out like this. So we have a suitability function here. I've chosen, this is a common suitability function for people to try in these models. And it just so happens that this is exactly the suitability function that fitness sharing matches up to. So fitness sharing is doing the exact same thing as what I'm showing here in this IFD plot with suitability. And so the idea here is I've got my 4 patches, and they all have this kind of hyperbolic curve that starts at a different point, because that's the breadcrumb rate that the person just is almost not even noticing there's ducks there. They're just throwing in breadcrumbs regardless of how many ducks are there, and they're throwing them in at a constant rate. That constant rate is the numerator of this hyperbolic function here, and the denominator is the number of ducks at the patch. So this is the best quality patch. So if you have 1 duck, that 1 duck goes here and nobody goes over here. So these will all have, so that 1 duck will go in, and maybe it'll actually be here if we're gonna make these discrete. And then these will all have 0. These ones that have 0, we're gonna call them truncated patches. So that's just a term that we use in the literature. Truncated patches are patches that no one's in. But this patch has an occupancy. Now the second duck, where do they go? Well, if the second duck goes here, then they get a reward that is still higher than all the other patches. But then the third duck, where does it go? Well, if it goes to that first patch, that reward is now lower than an alternative patch. So instead, there's a good chance it'll go here instead. So because of how this works. So now you're gonna have 1 duck, 2 duck, the third duck will be here. And the fourth duck, when they look at all this, the fourth duck says, well, maybe actually this is the highest, considering the other ducks that are there. And this process goes on, gradually populating the formerly truncated patches. So as a low population, so what you really get here, and this is what I've drawn down here, is this equilibrium suitability level, which gets lower and lower as you add more and more population. So if you've got a very high population, you get no truncation. Everybody populates the patches, but the population at each patch is proportional, or at least predicted by, the quality of that patch. So a high quality patch gets the most individuals. A lower quality patch gets the second best, and so on. And all of these add up to your population size. And I want to point out here that this equilibrium payoff, every individual duck, even if you're at the highest quality patch or the lowest quality patch, you experience the same rewards. So you're not changing the rewards to the ducks, you're changing the number of ducks in the patch. And so you can think of this as, this is almost like a cover charge across different late night venues that you could go to or something like that, this thing here. And so if there's a market cover charge, then that sort of affects how many people come into that location. And so everybody might want to go to the top quality place at first. And so they're willing to pay a high cover. But once you start getting a lot more people in there, then maybe the suitability of the place becomes less and less, and it gets so crowded, then now they're not willing to pay that top cover, and they're now starting to go to another location that charge a lower cover charge. And so this keeps going on until eventually you find that the best place in town has got the most people at it, but they're charging the same cover as the worst place in town, but very few people are at the worst place in town. But that's just because there weren't enough spots. People who wanted to go to the best place had to go to the next best, and so on. So that's kind of what we're seeing with the ducks. Yeah.
Is this how you would say Google Maps does its route selection as well? It can generate like 2, 3, or 4 different routes, and I guess time would be the objective, minimizing it.
Well, I would say that in that route selection, that's just a general optimization problem, and there's a bunch of different plain ways, genetic algorithms included, and other heuristics in order to sort of figure out the optimal. This is sort of saying that if you're using a population-based approach to distribute your attention among different alternatives, then the IFD provides a way to do that resource allocation. So a lot of people use the IFD. I don't know if I comment on that down here, but like I have a lot of colleagues who use the IFD to do load balancing, for example. So there's computer systems where you're trying to figure out, you've got a stack of web services, and the next traffic comes in. Which web server node do you send it to? And people have built load balancing strategies based off of the IFD and figure out where to send them next to try to get the lowest latency, for example, to serve that request. There are robotic cases as well, where you're trying to excavate some area and you notice that there's so many robots over there that hardly anybody's doing anything. So if you have a suitability function that can be experienced by a single robot without a central coordinator, then if that robot can go over this area and detect, like if the suitability is like time since I was last able to actually use my shovel, if that gets so long that it becomes an unsuitable environment, then it might search. And if it finds another one where it can use its shovel more quickly, it'll stay there. Otherwise, it might come back. So there are all sorts of heuristics that are based off of this concept here of the IFD. And for those that are really into optimization, if you're familiar with Lagrange multipliers, Karush-Kuhn-Tucker optimality conditions, then if you solve a constrained optimization problem, so if you constrain this, so you add this constraint and you maximize, let's say, the sum of a certain set of values, then it turns out that that constrained optimization problem, those things that you're summing up, if you take their derivatives, those will be suitability functions. And at the constrained optimum, then you'll find a Lagrange multiplier, which will be this value, which will couple all of those derivatives together. So for those who haven't ever had to do a constrained optimization problem, that probably didn't make any sense. But if you have, if you're Lagrange multipliers or whatever, solve, f plus g or a plus b plus c of x, y, and z, subject to x plus y plus z is equal to some constant. Solve that, and the dual space solution you get will be exactly the IFD. So that actually hints that the IFD is maximizing something as well. So there are a lot of interesting optimization things going on here that are out of the scope of this discussion, but I'm just throwing them out there for those who are interested. You can sort of find that. But it was originally dreamed up, not thinking about optimization, it was just thinking about how do we explain the asymmetric allocations of animals we see in a habitat. And it turns out that this is really this. You can sit and do this experiment. You can throw breadcrumbs in and wait for transits to die out, and you can predict what an allocation of ducks you'll get, and it will be very close to actually what you see using the IFD. All right, so idea here, was there other questions? So the idea here is that at the IFD, you've got these suitabilities that equalize. So I picked 3 non-truncated patches. So it's important that they're non-truncated. And across all non-truncated patches, suitabilities equalize at the IFD. If I go back to the one that looks like fitness sharing, which we'll talk about next, then that's going to mean that C1 over X1 is equal to C2 over X2 is equal to C3 over X3. And that ties into other concepts that we've seen pop up independently in other disciplines. This is the so-called matching law in psychology. If you put a bird in a so-called Skinner box where it's got 2 levers, and if it hits this lever, then it gets a reward after a second, and if it hits this lever, it gets a reward after half a second. You can calculate reward rates, and that bird will hit both levers, but it will focus on the one that receives a higher reward rate, and the time that it spends with the higher reward rate versus the lower reward rate will be described by the so-called matching law, which will be this distribution. Likewise, in economics and microeconomics, there's a so-called equimarginal principle that says that the if across all of your opportunities to spend your finite time or your finite budget, that's really what this is. You can think of this as, this is my finite, this is how many dollars I get per paycheck. These are all of the different things I could spend that money on. And the way in which you allocate your dollars, microeconomics and consumer choice theory would predict is actually going to fall along one of these things as well. So this is also an equimarginal principle. It's the marginal returns, the gain per investment. So there's a lot of interesting interpretations that you can get out of here. And and the other cool thing when you look at this, you can think of it as a game. If you think about the game across each duck, the IFD is a Nash equilibrium. Now see if that makes sense to you. What happens if you're a duck, you're sitting there, you're eating your breadcrumbs. So every fourth breadcrumb you get, and then everybody else gets the other breadcrumbs. If you decide to move, if you're at the IFD and you decide to go to another patch, what's going to happen? Well, everybody you leave behind, they're going to benefit. Wherever you go, they already had the reward rate you were getting. And now you're going to ruin it for you and all of them. So if you move to another location, then that unilateral movement, if nobody else also moves, then that's going to be bad for you. So the IFD is a Nash. But what's also cool about the IFD is that it's also Pareto efficient. So if anyone does better, so if that's one thing, if a duck decides to move, that's one thing. But what if I go in and I grab a duck and I move that duck somewhere else? Well, I have now made it better for all the ducks that that duck was competing with. But in doing so, I've made it worse for all of these ducks. So the only way for an external global party to make things better for some ducks is make it worse for others. So it's Pareto efficient. And the other really nice thing about that for us is that it maximizes resource exploitation. I'm not going to go into this as formally. This kind of goes back to that Lagrange multiplier stuff. So like stuff that you don't put Lagrange multipliers in the muddiest points. Like that's not a topic that we cover in this class. It was just a tangent. Perhaps I shouldn't have even brought it up. But what I do want to point out here is that we can go through logic here where the IFD, this allocation, maximizes exploitation. So if there's, so you can imagine what are different ways the ducks could allocate. Everybody could try to go into the highest quality patch, but then they'll push the suitability way down, and then all of these breadcrumbs will be wasted. They'll just be thrown out, and nobody will be eating them. This balance here actually maximizes the use of these breadcrumbs. So it's, here it's kind of trivial because there's no truncated patches, but this chooses which patches to truncate to ensure that the untruncated versions, the ones that actually have allocations, are maximizing the use of the provided resource. And that's really great for us if we're talking about multimodal, because if we can reallocate individuals in our algorithm, if this helps to ensure that they're going to the highest fitness peaks first, and once you run out of high fitness peaks, they'll go to the next highest fitness peaks, and then the next highest fitness peaks. So if you have enough individuals, if you can pay the computational cost, you'll populate all the peaks. But if you don't have enough individuals to populate all the peaks, you will have enough pressure that it'll be most likely you're going to be populating the high fitness peaks, and then the next, and then the next. So it creates a nice ordering when we're doing our multimodal. But let's see that in practice. But any questions about this general narrative here? I feel like even though the multimodal is couched as an evolutionary algorithm, really the way individuals move around is much more like this. In fact, this is exactly the formula they use to decide how to divide up fitness. Yeah.
Yeah. So given this, the fitness criteria as a CI by X, is this like same as we can apply for a knapsack algorithm or optimization? Because that is also in a combination of having at a particular weight, but given in a particular numbers of the thing.
Well, so I guess there's two ways to answer that. if you think of the knapsack problem as a multi-objective optimization, where I say I want to maximize weight and profit, then you can apply this to the spreading across the Pareto frontier. But then I feel like your question is more like, well, let's not think about let's sort of try to figure out a kind of a way to blend those objectives.
Yes, so that it can be in a similar way where we can choose anything and it gives the maximum profit, unlimited.
Yeah, it may be hard because the thing about the knapsack is here you are kind of putting ducks into sacks. And so it's like you're deciding where the duck goes. But in a knapsack problem, you kind of think about the things you're putting into the sacks. They're the ones carrying the fitness. Where here, it's almost like the sacks are carrying the fitness. And so you can probably build an alternative knapsack problem. And there are multi-objective knapsack problems, you have multiple sacks and things like that. But almost all knapsack problems, the core point is the things you're putting in earn you profit. Here, it's where you go and who else is there is what profit each individual gets. Okay. IFD, suitabilities, let's see how that plays out. So, with all of that, we want to preserve global diversity by creating these niche preservation techniques that have this negative frequency dependent selection. The oldest and most classic versions of these are fitness sharing, which is exactly the IFD applied to evolutionary algorithms. So the idea here is you calculate some original fitness, which is agnostic to how many others have to already landed there. So that's the fitness based on the objective. That's how high quality this design is based on the external objective being given to us. And then we count up how many are in a neighborhood that we have to define how big that neighborhood is. So there's a hyperparameter coming. But if we count up how many people or how many other individuals are here, then the fitness that this individual receives will be the fitness it would have received divided down by how many others are very nearby. And that's so-called fitness sharing, and that's just a suitability function. So when the rubber meets the road in the computations, well, how do we figure out who's around? So we have to have a niche count function, so called NC here, which is going to, maybe I'll just uncover this already here. So this niche count here, I'm going to figure out, and this is very generic, who to count up. And so there is going to be this sharing function which determines whether an individual is close enough to be counted. So this sharing function, you can think of it, so it's passed for every other individual in the population. So we're individual I, and we're looking at every other individual. And in this case, just for convenience, you would include the current individual because their distance is 0. You calculate the distance to that individual. In fitness sharing, it's very often the genotypic difference, the difference in the decision variables, but you can also make it phenotypic difference. So that's the difference in the objective values, and that applies for multimodal. That doesn't apply for multi-objective, because in multi-objective, these are often similar rank. So depending on your application space, you can decide which distance you're going to use. But you get that distance, and generally this function is going to be something that is going to be close to 1 if for nearby individuals and close to 0 for far away individuals. And this is one example of a generic sharing function that you can apply that gives you that. So this 1 minus distance divided by this hyperparameter sigma share. So that distance sort of defines the nominal distance where those outside of it are not counted and those inside of it are counted. And so if it's got this alpha parameter, which allows you to sort of create a soft kernel of penalty that smoothly dies out, it doesn't have a hard wall. But if you take this alpha to infinity, it then becomes a simple count of, are you inside the hyperparameter or outside the hyperparameter? And if you are inside it, if you're this close or closer, then you get counted. If you're outside, then you don't get counted. And so that's the idea behind this kind of soft fitness function here. So the closer you make this to 0, then the softer it gets, and you start including contributions from others. The closer you make this to infinity, then you end up getting a hard cutoff where everybody, sorry, it's not you, sorry, if the closer you make this to zero, you start penalizing inside sigma share in a nonlinear way. So if you're right next to me, like if sigma share is from me to the door, then you get a higher penalty here, than here, than here. Once you hit the door, it goes to zero. But if you take alpha to infinity, then it's the same penalty from me to the door, and then it's zero outside. All right, so that's a basic fitness sharing here. And then you can apply this to, you just calculate this new fitness and then let your original genetic algorithm rip with this new fitness. And then the dynamics of an ideal free distribution just redistribute everyone across peaks. Questions about that? Yeah, go ahead.
Are we calculating sigma share?
This is a hyperparameter. So you define it ahead of time. So based on knowledge of the optimization objective, so if it's a multimodal, you'd say, I don't think modes, or at least I don't care about modes unless they're at least sigma share away from each other in genotype space, or sigma share away from each other in phenotype space. So you have to kind of, this is a parameter you might have to play with. That's one of the problems with this method, is that you may not know that ahead of time. And so it would be great if we had a method that was parameter free in this case here, but you might know that info, or you might be willing to play with it. Okay.
So that's how it detects like how many peaks there are going to be.
This will end up defining, so the combination of population size and this distance tell you how many peaks could be covered. So if you had thousands of individuals and a small sigma share, you could cover lots of, but if you only have a few individuals and a small sigma share, then you're probably going to, have those few individuals are going to, they're going to be packed close to each other on like little nearby peaks, but you're going to miss a lot of other peaks. So it's the interaction of those two. Okay, a big problem with this algorithm is this, because this requires pairwise comparisons. Every time you calculate the fitness of one individual, you have to iterate through all of the other individuals. And there might be some memoization you could do. So you might be able to say, oh, I've already calculated this distance, so I can calculate all those distances once, and then I can use them throughout the whole generation, so that you still have to iterate through every other individual. So that creates a computational problem. And so variations on fitness sharing have tried to address that computational problem. So one of those cases is to use something inspired by kind of k-means clustering, so just clustering algorithms. So we could say, well, let's say there's a hyperparameter k, which is our guess for how many modes are out there, or at least an upper bound on how many modes we think that we want to care about. Well, then we are going to use another set of hyperparameters, dmin and dmax, which are distances in genotype space, to create seeds for those k clusters that have this criteria and those seeds are individuals. So we're going to say that we're going to try to look across the individuals in our population, and we are going to create a new niche count based on these cluster seeds. We look around everyone that's currently spread out across there, and we say dmin, that's the minimum distance between any cluster centers. So if you're next to each other, then one of you will be a seed and the other one will not, if they're right next to each other. And then dmax is the maximum distance between the cluster members and their centroid. So you end up creating these clusters where an individual is selected as the seed of their cluster, the centroid of their cluster, and then dmax umbrella around them, and then those inside dmax, those are going to be individuals that belong to that cluster. So you use these as guidelines for creating these k clusters. And then what's great about that is now that you've got an owner of each cluster, you can do a count based on just that cluster. So I still do fitness sharing, but instead of calculating a per individual count, I do a per cluster count. So if I say ahead of time, I really only think there's going to be 4 peaks, then I find my 4 cluster seeds, and then I do the count just for them, and then that applies to anyone in that cluster. So that this NC is not the number around individual I, it's the number in individual I's cluster. So you only have to do this calculation once per cluster, which if you have lots of individuals but very few clusters is not very much. And then you then scale that by, this looks, this is certainly similar to the sharing function we saw before, where DIC, that's the distance between this individual and their cluster centroid. And so you have a D max, which is like 2D max, that's kind of the diameter of your cluster, because D max is the radius from the centroid. And so you compare your distance to the centroid to this diameter, and you scale it by alpha. So again, alpha plays a similar role as it did in the previous one, and that's how you do your shared fitness. So as you make K go to the number of individuals, this basically becomes the old shared. Because at that point, everybody is their own centroid. And for every centroid, you have to do a count. But here, if you have lots of individuals but very few centroids, then you have to do very few counts, and it scales a lot better. So that's the idea behind clustering instead of pure fitness sharing. It's just to make things faster. Does that make sense? We still have lots of hyperparameters, so Dmin, Dmax, K. So then another approach is clearing. So the idea here is we're going to, this is I think our last fitness-based approach. We're going to sort by fitness and then take another hyperparameter, our K best solutions. And then we have another hyperparameter, sigma clear, which is similar to sigma share. And we say find all solutions within that of each one of these K best and set their fitness equal to 0. This is the clearing. So we're not going to take the fitnesses and divide them by some smooth amount or whatever. We're just going to say we take the K best, we then put a sigma clear circle around them. Anyone that is within that of one of the K best gets their fitness equal to 0, which effectively kills them because the selection operator is not going to reproduce them. It's going to then use their slots for others to populate the population. And then we can do that based on the next best K and the next best K and so on. And we repeat that until we've considered all n of these. Yep.
What if the K's lie within sigma clear of one another?
I mean, it's that could happen, and then so one of them will get zeroed, and that will, so because even if it is in fact it will happen a lot at first, because you might have a fitness peak, and it might be that you've got a bunch that are near the top of this fitness peak, and everybody else is down here, and so these might be the top K, and so this one will be selected first, and then these all get killed. And then you keep doing that. But then what's nice about that is the one that's left over, they are the only one on top of that peak. So that can't happen. And I think that's by design. Yeah.
You like repopulate things that one at the peak, because otherwise, or like you don't like making like individuals in different places, because otherwise you're like not exploring the little.
Well, yeah. After you set fitness equal to 0, you then let the selection and crossover and mutation operators do their job. And so if you set their fitness equal to 0, everybody left over, which hopefully should be a bunch of individuals on top of peaks, they're all going to be the ones selected to be the parents. And so they're going to be the ones who get crossover and mutated. And so that you will get individuals near them. And if the mutation is strong enough, hopefully you still get a few. Like you might end up getting a few that are down here. So that's the other interesting thing about it is if everybody stayed up in the here, you might have a couple of low fitness solutions, which now become contenders once you kill off all of these and all of these. So that now you're going to explore nearby these two, But then this one has an opportunity to move around as well. Maybe I should have drawn it over here so it could move this way. All right, so that is our clearing approach. And then there have been alterations to any questions on the basic clearing here? So you just sort. Because it's sorting, we're going to see like an n log n instead of an n squared complexity coming up there. And then an alternative that people have tried is different ways to reposition. So kind of getting maybe close to the question that was just asked. You could do clearing like normal, but then you've got all of these, a lot of individuals, especially at first, will get their fitness set equal to 0. And that just seems like a waste. Because now you've got a bunch of these individuals that just, they're like, could we have done something with that? Rather than depending on recombination and crossover and mutation from the parents, maybe there's something we could do more intelligent with those. So the thought here is to say, if you have a cleared solution, a fitness 0 solution, within 1.5 distance, sigma clear distance of one of the remaining solutions after this clearing process, then just randomly regenerate an individual that is a little farther away, that is between 1.5 clear and 3 clear. So we're going to move them a little bit out. So they might have been within a sigma clear of this solution, but there might be another solution that they're within 1.5 of. And you can take one of those cleared ones and then move it within 3. So you're kind of choosing a little radius and just pushing them away a little bit, adding a little bit more space, and then recalculate their fitness. So rather than just, that would sound like the floor is lava type of effect. So if you think about it, it's like once you step on one of these K solutions in the clearing, you're immediately dead. Now it's like, well, if you were kind of close to them, we're going to give you an opportunity to shift away and then see how well you do. But then they do clearing second round on those. And anyone who survives that maybe has done some interesting exploration, will be a good candidate for the next one. And that does maybe improve performance, but it attempts to discover these interventrous patches, but it's a lot of extra costs. You got 2 rounds of clearing, and you have to randomly generate these new solutions in this tight round. So you pay a lot to get this more intelligent exploration. So I bring this up just because when you're looking at these, you see all these kind of heuristic approaches, and it's going to be very tempting to say, oh, I could come up with, like, you could imagine all these different ways that you could diversify the population. But you have to think about the computational complexity. And so all of the ones that are in the literature that work really well, they have this balance between a clever way of spreading things out and not being so costly. Because if you've got 1,000 individuals and you're running 100 generations, you might have to do this lots of times. So you don't get a lot of points for being like super, super clever and complex. It's got to be simple and fast, but then also achieve the result. All right, questions about clearing? Okay, so then we can switch over and say, you don't have to be fitness-based, you could also be selection-based. And so these are modifications to selection operators. The previous ones were modifications to fitness calculators. These are modifications to selection operators. Yeah.
Is that like just the only 2 clusterings that we have for fitness-based?
Well, those are 3 common modes of clearing or of fitness-based options for diversity preservation. Fitness sharing is sort of the oldest, and then clustering, which is really just a modification of fitness clearing to have a tunable parameter, which reduces the cost. It gives you kind of a speed accuracy type of trade-off. And then clearing and modified clearing is it's just an extreme version of fitness sharing where only one individual gets to take the fitness and everybody else gets pushed to 0. So it's like a discrete version of fitness sharing. So really, I've shown you 3 versions of fitness sharing, just with a different way of handling the individuals around. There are other ways, like I said, like this modified clearing. There's a paper that I shared by Singh and Deb, where they introduced this modified clearing, and it has results. And you can come up with other ways to do variations of this. But generally speaking, fitness-based approaches to diversity preservation are costly, computationally costly, and so they're more modern approaches usually use more selection-based or archival-based approaches.
No agglomerative clustering works.
There are other ways you can come up with. I've just shown you one way that clustering has been applied as a modification to fitness clearing, but there are a bunch of if you just look at a data set, you say, I would like to cluster this, I'd like to do an unsupervised clustering of these data. And you can imagine that there would be a way that might be useful in multimodal optimization. It probably would be for one iteration. But then once you have to think about that, but I need to do that, I might need to apply that to every individual and every generation. And all of those costs add up. So you have to say, well, what's a heuristic that gets kind of close to that? And so there are other ways that people have tried, but you always run up against this, that you don't want to be too clever on an iteration scale, because you really have to think on like an algorithm scale. All right, so let's go a couple minutes here. Let's at least introduce what I mean by selection-based approaches. So this is, there are two types of crowding approaches we're talking about. One is only for multi-objective. The other is pretty much only for multimodal. And I'm just probably only going to get through this multi-objective one here, and then we'll pick up with this the next time we meet, which I guess next week is spring break, so it'll be after that. But unless we did do the math wrong, well, anyways. So crowding by distance here. So the idea here is in a multi-objective optimization, you do your Pareto ranking. So this is really for Pareto ranking. And then you calculate crowding distances for ties. I say it's only for Pareto ranking because that's where you get a lot of ties, because it's a discrete fitness. So you can get a lot of things at the highest rank and a lot of things at the next highest rank. So for each rank, then you look at all of the individuals within that rank. And so for each objective, you sort within that rank those individuals by that one objective. But you do that for every objective. So you can say, of all my non-dominated solutions, I'm going to, if I have 8 objectives, I'm going to create 8 orderings. And so I've got an ordering in objective 1, objective 2, and so on. So then I'm thinking within each one of those orderings, then I am going to create a crowding distance that is going to be assigned to that individual. And this will end up summing across all the objectives. So if your individual happens to be at the end of one of these orderings, any of the objectives, it's going to get an infinite crowding distance. So in other words, we want to keep that individual there. If they are at the end, then we cherish those individuals. So this crowding distance, the highest crowding distance ends up being better. So it's going to break ties. And if any individuals at the end of any objectives ordering, we want it to win that match, that tournament selection. Otherwise, if they're in the interior, we're going to look at where in objective space its neighbors are, the next best and the next worst objective. And then we divide that by the very best that we know about in this objective and the very worst we know about in this objective. And we create this score, this normalized neighbor distance. And we add that to the accumulating crowding distance for every individual. And so what this is going to do is this effectively adds up the space around every individual in multi-objective space. Creates a cube that's around every individual in every direction, and it creates sort of the volume of that cube, and that's what we're going to use to break ties in tournament selection. And that will hopefully take clusters and spread them out, and individuals who are alone, leave them alone. All right, so that's an example of a selection-based approach when we're keeping fitness alone, but we are changing the way the selection operator works so that we almost add another objective that's hidden here where the objective is spread out. And that's what we'll leave it, and we'll pick up from there. So any other questions, feel free to come up. Otherwise, if I did my math wrong or right, I think next week's spring break, in which case have a nice spring break. And we'll see you next time.